So we are very happy to have Monica from Caltech, and she will tell us about the GNS story of holographic baby universes. Please start.
For the invitation to give a talk at Berkeley. I wish I can visit there in person, but I'll try my best as if I am there. Today I'll talk about a GNS story of holographic baby universes, which will be based on my two papers with Elliot Gesto. First, I'm going to, after motivating basic facts about baby universes, going to just explain the formalism of a GNS construction that's based on this first paper. And then we'll move on to its application to understand more physics about baby universes and ADS-CFT based on this paper. So baby universe is, roughly speaking, a new piece of space-time manifold that becomes either attached in a connected way or in a disconnected way, which individually will be giving wormholes that branching out or having isolated quantum islands. These are work done by Giddings and Strominger after Coleman suggested about its possible existence in quantum gravity. And in their papers, they talked about creation of and annihilation of the baby universes and how it somehow contributes to the Hilbert space of the theory. By that, they analyze the Hilbert spaces directly and try to understand it a little bit better. In particular, they propose a third quantized model, which allows for topology changes in the bulk of a Lorentzian spacetime. For the purpose of the talk for today, when I'm applying to baby universes and later, I'm going to utilize the fact that we can use this as a topology changes of the bulk. In particular, in getting Strominger, they considered particularly for a model that uses an axion field coupled directly to the gravity. And they showed that some topology changes explicitly appear in that context, and further exposing the baby universe branching. In that aspect, we're going to remember this and try to utilize what we can do to understand baby universes and its Hilbert spaces, but in a more algebraic approach. For that, unlike their paper, I'm going to focus on Euclidean baby universes, since Lorentzian structure is harder to understand, at least for current Stanford algebraic approach. And by having Euclidean baby universes throughout the talk, it will be dimension independent. So it doesn't have to be in any dimensions for this approach to make work or any analysis to stand. However, I want you to really have in mind that we want to, in the end, want to understand 4D Lorentzian theories. So we can think of it as this analysis of 3D Euclidean geometries with the time direction, where we can have a traditionally having Hartle-Hawking state going through the Wheeler-DeWitt equation to annihilate the Hamiltonian description one can have coming from it, so that you're considering the superposition of 3D geometries coming from this Hartle-Hawking state. So in turn, it's kind of an ensemble of a theory, which we'll come back to it by the or near the end of the talk. And in here, as I was going to emphasize, we have diffeomorphism invariance coming from this theory. Yes?
I have a question. So this Hartle-Hawking state is a quantum superposition, right, of 3D geometries. I mean, I can, yeah. Why are you saying that it's an ensemble?
Later on, I'm actually going to show that you will not want to have an ensemble, and there will be a pure state coming from it, and there's no further additional subtleties attached to it if you want a one-dimensional Hilbert space for baby universe contributions.
I guess I'm just not understanding. It is a pure state to start with, right? As you wrote it, it's already a pure state, and I'm sort of not understanding why you're attaching the word ensemble to it.
Oh, no, I'm going to actually just later talk about it and how the pure state is coming from it in a more algebraic context to make it work, which is, it will come more clear in the end. It won't be that subtle.
Yeah, I think my problem is that there seems to be a subtlety here that I'm completely missing, which is, I mean, it just looks like.
I'm not actually saying anything of subtlety here. It's just that I'm going to really address from operator algebraic approach. What does it mean to have a pure state, which will yield directly into back to allowing to have a Hamiltonian description of the theory is what I really want to motivate it's a motivation intro, so trying to make it more vague.
Monica, is what you're saying is that some people would argue that this sort of a this baby universe situation is going to lead to an ensemble, and you're going to argue that in fact it doesn't?
Yes.
Does that appease you at all, Raphael?
Yeah, I'm just trying to really just motivate that.
Appease.
It was not supposed to be that deep yet. All right, so moving on from it, as I was emphasizing, you're going to take an algebraic approach to understand this phenomena of a context. And then I'm going to focus on how you're going to do so by using the GNS construction for this approach. So as nicely, holography has led us to have bulk and boundary duality. We can express any local bulk operator in this context to express as boundary operators in ADS-CFT by smearing over the entire spatial slice or a compact spatial subregion. And these operators, we can form it as an operator algebra. By that, I mean, we're going to first take quantum error correction perspective to it. So these local bulk operators will be explicitly defined only on the code subspace of the physical Hilbert space of the boundary CFT. By that, I mean, it's going to require this Hilbert space attached to the theory to describe this quantum field theory together with the operator algebra context. And for this Hilbert space, I'm going to take it as general as possible. By that, I mean, you're going to be either having finite or infinite dimensional Hilbert spaces, and I wouldn't care one or the other. Though I want you to more think in terms of infinite dimensional context, as that will be more difficult to do so, as I have more of a Rishi leader picture in mind, but it wouldn't be needed, as it'll be just generic. Anything will be applied in this context. And from there, I'm going to try to use then this operator algebra to describe the local operators of the quantum field theory that we were interested in. By that, I mean, stereotypically what we usually use is a von Neumann algebra. By that, I mean the local operator algebras of the quantum field theory is generically forming a von Neumann algebra. Especially in infinite dimensional cases, it'll be generically type 31 if you know about the classification of the von Neumann algebra, which is nothing more than an algebra with bounded operators that contains an identity closed under Hermitian conjugation, since we're in quantum, and its double commutant map back to itself. By that, I mean, what we can really think of that is when you have some sort of entangled wedge or some region, we can attach the operator algebra there, and its commutant will map there. And when you double commutant it back, it'll come back to this so that it'll actually make sense as an entanglement wedge. And that's the special condition that von Neumann algebra require. Now, as nice as von Neumann algebra is, it is more of an advanced feature of an algebra. By that, I mean it is a state dependent of an object. So von Neumann algebra is an operator algebra with explicit description of a Hilbert space required. And further on, it'll require ground state of the level of state description of the Hilbert space. And we traditionally call that in mathematical sense of cyclic and separating state, which you can think of as injective and not quite surjective of a state. And as you can see, that it will be then state dependent of an object. Now, why am I emphasizing that this is state dependent? Okay, that's difficult to deal with it in terms of algebraic approach to understand. By that, I mean state is a very nice object in physical sense. That's what we'll be measuring, and that's what we need to actually utilize a theory to understand. However, compared to just operator level, it demands a lot more of understanding and more complicated of a structure. So what I'm trying to really move it for the formalism is that we will require less to do the analysis and move back to understanding of a state. So that when we have just operators, it's more easier to deal with. You can have OP extensions and get correlators. It's easy. However, you will need the state in the end to understand better. And what I really want you to have a thought in mind at the moment is a tensor network, which is not defined at the level of a state, but more as an operator direct pushing of a method. So it's more a course of a system, if one might say. So I want to put it as a system that, without understanding the entire state mapping between the bulk and boundary states, which is considered a state pushing here, I'm going to move to this formalism where we can have operators acting on the bulk algebra to be mapped directly to the boundary operators, and then get the information to get back to the state.
I
was pointing out, yes?
What exactly did you mean when you by the von Neumann algebra is state dependent? Like what notion of state
dependence? It requires
dependence?
a description of the Hilbert space, and further on, you need to understand as an isometry already defined at the Hilbert space level, which comes with the state understanding. Like bulk state to a boundary state, that isometry has to be done at the Hilbert space level with the von Neumann algebra, and you require the ground state, and that allows you to do so. And for an operator pushing, you would not require to do so, which is what I'm trying to build.
Okay, thanks.
Great. So far, then what we had in mind was a von Neumann algebra of operators acting on Hilbert space directly with states. But now I want to really move into is an object that's not requiring state dependence quite yet. By that, I mean, we're going to use Cstar algebra. It's nothing more than a complex algebra with a Neumann involution without the notion of Hilbert space defined yet as an operator algebraic level. And then we're going to use operator pushing map, which is defined within the level of operators, and then construct the Hilbert space by using the GNS representation technique. And we're going to utilize the concept called KMS state to give you the ground state that'll give rise to the ground state or vacuum of the quantum field theory or gravity. So before jumping onto explaining GNS construction, I want to generally propose or give some idea so that I will give you a dictionary between the operator algebra perspective and our course of interest of the theory in quantum gravity. So as I was emphasizing, I'm going to now move into the Cstar algebra to be at the operator level instead of state level. So we're going to assume those existence in the bulk and the boundary level, which will give rise to the local operators in the bulk and boundary accordingly in the quantum gravity sense. And I'm going to require a Cstar isometry, which is nothing more than a map between elements of the Cstar algebra level of between the bulk and the boundary. By that, this is not exactly the isometry that's strong enough to hold in the Hilbert space level yet. So what I require is really the operator pushing map. And from here, we're going to utilize the GNS representation to build onto the isometry that we are usually familiar with between the bulk and the boundary, so that we'll have it to the state dependence afterwards. And we're going to also require a strongly continuous one parameter group of isometries of this boundary algebra. It's quite a mouthful, but it's really nothing more than a Hamiltonian evolution. And that one parameter is commonly just the time, or any of the parameter that you'll evolve with. And on top of that, we want to actually build a vacuum in the end, because we would require a cyclic and separating state in von Neumann algebra, or just a thermal vacuum in our field theory. And for that, in Cstar level, I'm going to utilize KMS state, which I'll explain with the GNS construction that I'm going to explain very solidly, which will give rise to a thermal vacuum, but at the level of the operator level. And once this is all done, and let's say you can do the GNS construction, which I will explain shortly, then you will be able to bring back to regular vacuum and the von Neumann algebra description with the Hilbert space attached. Then once you have that, you can have commutant and double commutant. So the regular story will stand, that you can get the other side of the wormhole, the other boundary, and everything will follow through, which I will demonstrate how you can also get the von Neumann algebra from this process. So that kind of looks like a good dictionary, but I want you to have an easiest example in mind, which I will use, again, the tensor network, since that's the easiest thing utilizing operator pushing type of map. Yes?
So just to make sure I understand, when you say that the, well, when you talk about state dependence of the algebra, what you're referring to is just that you need to pick a cyclic and separating state, right?
Yes, and also the isometry between the algebra is not requiring the Hilbert space. Because Cstar algebra on its own does not require a Hilbert space to work.
Yeah. So you're saying you want to somehow now going back to ADS-CFT, what you're somehow trying to do, I think, is distinguish between the mapping of operators. So there's some quantum error correction of operators, which doesn't yet require you to commit to a particular vacuum state in the bulk.
Correct.
But let's say that we have global ADS, and I look at the vacuum state on the boundary. So in that case, something is presumably going to happen that lets me say that I'm going to have the vacuum state in the bulk. There shouldn't really be an ambiguity in that case.
In fact, I'm going to deduce you that you'll naturally get the vacua in ADS-CFT context naturally out of it when I utilize the GNS condition. In fact, I'm going to explicitly demonstrate how this is literally a generalization to include for the infinite dimensional context. It's just a little less required so that we can utilize just in the everything to be done in operator level for analysis, so that we cannot do all sorts of difficult process, but can move on to back to our more casual setting. And so as an example, I want to have in mind its easiest motivation part is a tensor network. Tensor network does not require much things, as happy code infamously say. It just requires these tensors through as an operating map, and usually comes a bulk and the dangling boundary nodes. And all we are given with how it's prescribed and how it gives us like a pentagonal tiling or hexagonal tiling or mixed of those, which is just given as an operator pushing map. It does not require state. In the end, when you're now analyzing to understand the physical model, you need to have a state. But before that, you were just given with an operators. So that's what I really have in mind here as like an easy toy model, so that when you have the Cstar algebra on the bulk and the boundary now, which is not requiring much of a state, then you have basically the operators of the bulk and boundary node respectively in this tensor network. And Cstar isometry is exactly that map that goes from the bulk to boundary as an operator pushing map. And tensor network does not necessarily require Hamiltonian, but one can always have a Hamiltonian that's sufficient to evolve together into to understand the Hamiltonian understanding of the theory coming thereof. And that will be exactly the same thing as earlier mentioned, the strongly continuous one parameter group of isometries. It really sounds like a mouthful. I will demonstrate that this is exactly just Hamiltonian evolution in finite dimensional context. And then later on, everything's just identical and follows through. So by that, I'm going to explicitly construct so that we can get schematically how the bulk to boundary duality works out of. So first, I assume the Cstar algebra on the bulk and the boundary. That's the only thing I really required. And the one more thing I was telling you was that I'm going to require this thing called KMS state and going to have a Cstar isometry. And in order to continue to have an isometry after constructing the Hilbert space by utilizing a GNS construction, I'm going to require the pullback of this KMS state to be existing on the bulk, which it's very easy to do so. Then those will be mapped directly one another to make sure that there is a ground state or a vacua to exist after having a GNS construction performed, so that you'll have a regular isometry that we're used to as a map between bulk and boundary with the Hilbert space attached that will guarantee the vacua between the two, and the map will be perfectly normal as we know before. So this is what we're going to really establish in the end, coming with the both algebra with the Hilbert space with explicit isometric mapping. And further on from here, I'm going to now show you that this will directly give you the von Neumann algebra, and it does not require any more additional analysis or computation, and you'll just get it out of it. So that's a lot of promises. So let me actually demonstrate how you can do that in the easiest way possible for the GNS construction. So as I was keep saying, you'll only require a Cstar algebra, the operator level type of an algebra. So how do you prepare a state? A state on this algebra is a linear functional, so that we can have as a non-negative real number and containing the identity. That sounds very natural. So let's say we want to build a Hilbert space coming from this algebra. The most intuitive way to do so is, well, we can define an inner product between the two of this and get directly the Hilbert space out of it. That sounds very reasonable. And we can build an inner product in the most easiest way possible, for example, as just left multiplication directly. Now, this will have a little bit of problem because you can have a self-vanishing type of things to be included. But we can make it well defined by quotienting those out directly. Then you can get the resulting Hilbert space coming from this, endowed with the left multiplication, and everything will be well defined. This will be one of the easiest ways to build as a GNS construction. And this will be the GNS representation that allows this to happen. So what do I really mean by that is that the GNS representation of the state, what it does is that it just does purification of the state into a vector state. So you can write as this. And this will be the corresponding GNS representation of the state that you built as a linear functional. And this must look really familiar because this looks exactly like a regular quantum mechanical description that we're very used to. And this looks like exactly like a ground state. And we're going to build onto that so that this will actually indeed become that vacuum. By that, I'm going to now finally talk about the KMS state that's going to allow you to have such. KMS state characterizes the thermal equilibrium with respect to this Hamiltonian evolution. So in order to really explain this in the context that we are very familiar with in quantum mechanics, I'm going to have an explicitly a finite dimensional system as an example. So we have a finite n-dimensional system, then what we're given as an algebra is just n-dimensional matrices. And we know the Hamiltonian, giving an evolution very well, we just sandwich with e to the IHT and exponential minus IHT. Sounds very normal. And this is going to be exactly the strongly continuous one parameter group of isometries. It's just mathematical term that's going to be correlating exactly the same for it. And in quantum mechanics, we just take the Gibbs state by taking a normalization as a trace and considering its excitation as an exponential to the minus beta h with the inverse temperature beta to give as a unique state representing this thermal equilibrium. Now, this actually has an issue when you're trying to generalize this in the context for all general possibility, because trace is not always defined. By that, I mean, in most infinite dimensional, even though Neumann algebra cases, traces are usually not well defined, especially for generic type 3.1 does not exist. Then that's a problem because with this exact method, we cannot compute this Gibbs ensemble. But we can utilize this KMS condition, as I'm telling it's exactly the same thing, but in just more abstract sense, which allow you to have it generalized for all possible cases. So now you're given with the Cstar algebra in the same state. And then this Hamiltonian evolution is exactly given as the one parameter group of automorphisms. Now what we do is that we're going to have this analytic continuation of this imaginary point from 0 to inverse temperature beta, so that it'll be continuous on its closure, so that it'll be well defined and it's going to give rise to exactly the corresponding thing like a Gibbs ensemble, so that you'll be given with a unique state that you need. By that, it sounds complicated, but it's nothing more than having the GNS representation just allows to represent the KMS state. It's nothing more than a thermal state as a vector state on the Hilbert space, which was the vector state that I was telling you a little bit earlier as a vector identity looking at its ground state. In fact, I'm going to do a little bit better. I'm going to show you that this GNS construction with the KMS state will be nothing more than a direct generalization of the thermal field double construction. By that, I mean it'll be identical for the case for finite dimensional cases. It'll be just doing that carrying over to infinite dimension as well. So in order to actually demonstrate this, I'm going to first describe what thermal field construction is to juxtapose this for the finite dimensional Hilbert spaces that we can actually consider. So for that, our thermal density matrix is exactly the Gibbs ensemble. And as thermal field double, the name represents, it doubles the size of the Hilbert space. So it constructs a purification from one to the other by having this mixed Gibbs ensemble state. So what we really get is a doubled Hilbert space. We have H cross H. And in this very doubled Hilbert space, we traditionally write the thermal field double state as the vector state as this, which is a purification onto all the eigenbases of the Hamiltonian one can pick with its eigenvalues as the thermal ensemble. So from here, Let's now consider a GNS construction for the very same case and see if it does exactly the same thing. So considering a finite dimensional case for the GNS construction with a KMS state, I'm going to first assume the thermal density matrix is non-degenerate because that would be the easiest case to deal with it. Then for a Gibbs state, the thermal density matrix is invertible. What does that mean? It just means that the ideal of the GNS representation is trivial. So what follows there is that the Hilbert space is directly constructed out of this algebra, and this is isomorphic to H cross H. So what it really did was constructing the doubled Hilbert space, just like in the case for the thermal field double construction. And further, by its construction of GNS representation, the density matrix is now represented as a vector state. The outcome of that is that the GNS representation is really exactly doing the same thing as a thermal field double construction in the case for the non-degenerate finite dimensional perspective. So what I really want you to remember from this is that the thermal field double construction transforms any mixed thermal state into vector state. And this is exactly what GNS representation does with a KMS state. So all I want to really convey so far is that in order to have everything done for generically in context of infinite dimensions included Hilbert spaces, without considering the Hilbert space, if I want to start an operator level, all I need to require is a Cstar algebra in bulk and boundary and a KMS state. And with the formalism of the GNS construction, we'll take care of it. And further, so by doing this, what we really established to get is the Hilbert space of the bulk and boundary individually. And we create the bulk to boundary isometry at the level of the Hilbert space from just Cstar isometry. And further, we get a vector state for each Hilbert space. And that I was just showing that just direct generalization of the thermal field double state. So from here, what we really need to now reformulate to convince further is that you bring back to the von Neumann algebra. You're going to have a local operator algebra of quantum field theory, as I just showed you that you have a ground state already recreated back. Let's see how you can actually do that in the easiest setup. So recalling that the GNS representation purifying the state into the vector state, as I was emphasizing in the middle, you can have this state, and that's the state you get, kind of like a ground state as a thermal vacuum. And what I didn't tell you so far is that this is guaranteed to be cyclic from the operator algebraic analysis. In fact, it does better, that the action of this algebra on the state spans a norm-dense subset of the Hilbert space. So this cyclic property that we want actually extends to the bicommutant of the Cstar algebra on the entire GNS Hilbert space. So what it does is that it makes a double commutant mapping it back, and it guarantees you to be cyclic back. So this generates a von Neumann algebra without doing any more analysis. And the vector representative of the KMS state that you can have is this vacuum. In fact, what I haven't told you so far is that it indeed generates a separating vector for the Cstar algebra, thanks to Stromer. And this property indeed holds for the whole von Neumann algebra closure of the double commutant. So by doing no further analysis, when you're given with Cstar algebra, we can prove that this will give you a von Neumann algebra with a cyclic and separating state. And this, what we see, is exactly the ground state you get in the context of quantum field theory or quantum gravity in semi-classical regime. So that's great. So yes?
I think I'm still a little bit confused about what picks out the actual state. I mean, so for example, if I gave you 2 copies of the CFT, there I think are states that we will be happy with, where, for example, it's just a product state, and there's also a thermal field double, and there's lots of other states which are as entangled as the thermal field double. Which of these, are you claiming that something's being picked out here uniquely, or that if I pick a state on one side, I'm just gonna get a completion of it?
A particular entangled wedge, so it's in the setup that you can have a von Neumann algebra with a unique ground state, then it'll pick that up. Now, KMS state or ground state does not necessarily need to be unique in the sense of infinite dimensional cases. No one has proven that. But that one you can have as many of the cyclic and separating state as a thermal state one can have. It'll individually give you that back.
I think what I want to ask is a simpler. I mean, I'm not quite caught up. I think what I want to ask is, what are we given, and what is then constructed by this construction that you're discussing?
So if you're given with Cstar algebra of the operator level for bulk and boundary, and their operator.
So can I stop you there? Sorry, but what I'm confused about is for what sort of bulk and boundary. So are we given some bulk should I be thinking of some sub-region of the boundary and a sub-region of ADS?
Yes.
Or can I be thinking, for example, of the whole boundary? And if not, what's wrong with that?
Construction will tell you it'll work for anything, but the one I want to focus today is that in the context of ADS, you will have the sub-region to sub-region with no problem. Like entangled wedge within there, the bulk and the boundary will have no problem. That one will be given very well with the KMS state, and that'll give you the ground state as a vacuum.
Am I given, for example, let's say half of global ADS, half of the boundary, and I'm given the thermal density operator for that half, and then this will construct the global vacuum state?
If it recreates the whole thing, so when you have a bulk reconstruction guaranteed, then it'll do. But I'm not showing that bulk reconstruction always works. That's a two different thing, right? So in infinite dimensional setup, can you always have a bulk reconstruction? That I did not prove. But if you can have that, I can guarantee it to work.
Maybe, Raphael, your question is like, how is the region specified? And I think maybe the resolution is like your choice of operator algebra, the set of operators you're including will determine essentially how much of like the bulk, or if you're taking all of it.
Yeah, I think that's not really my question. I think my question is whether there is a claim that somehow a unique state is picked out, like, or yeah, I think I'm confused. What's the?
What I'm saying is that if you can have a unique state of the cyclic separating state, meaning if you are given with a unique state, you can, then I can pick that out. If it's non-unique, I can also generate for the individual non-unique cases. So all I did so far is that as long as you can have everything with the von Neumann algebra format, I could recreate all of that without using state dependence. Or is that not what you're asking?
I think I'm too lost. You shouldn't stop for me. If other people have questions, they should ask them. But if I'm the only one confused about that, then I don't want to hold you up longer.
There's also after the talk or tomorrow's group meeting, right? Yeah. Or you can ask in the middle so I can understand your question better.
Yeah, no, I think I'm just somehow completely lost. Yeah, sorry.
Okay, so moving on. Now that's the recap of the GNS formalism that I constructed together with Elliot Gesto in one of the paper for at least some of them. Now up till here, what we did, we're going to apply to in the context of baby universes, specifically in the context of ADS CFT. For that, we need to actually construct baby universe algebra, as so far the really core important thing one needed require is a Cstar algebra of the Vulcan boundary, right? And so from here, we're going to build this by dealing with baby universe, as I was in the very beginning telling you, to grant it as topology changes of the space-time in the bulk. So by having this creation and annihilation of the baby universes viewed in respect to as a topology changes, I'm going to build that as operations individually called connected sum and gluing, which will be a creation and annihilation in respect of the baby universe. And utilizing these boundary changes, I'm going to build the baby universe algebra. So this one, first of all, creation is guaranteed by this connected sum. So this picture is depicting how it actually performs. So you can think of that as that these red things are the conformal boundaries. And I'm depicting as an example with two hyperbolic handle bodies. And I'm going to punch the hole here and identify them and glue exactly together, which is a topological operation called connected sum. And this one is going to give you the baby universe creation, but one has to be kind of careful because baby universe can be created in two different ways, as I was emphasizing in the beginning. It can rejoin in. I mean, it can be connected to some of the pre-existing piece of a space-time manifold, but it can also create as a separate isolated island. So in order to compensate both possible things for the theory to be acknowledging both ways of existing, when it's just branching out type, we're going to have it as a connected sum between the pre-existing piece and the new one. And for the isolated type, we're going to connect the sum with the empty space-time, which will be a way to holistically have those in mind so that theory knows baby universe is created or not, whether it's attached or not attached. So this is a gluing operation. Now this is for the annihilation of the baby universes. And this one is easier as there's conformal boundaries. We identify them and glue them in together so we annihilate and remove one baby universe back to absorption. Now utilizing these—
Sorry, could I ask a question?
Yes.
So in those pictures that you've got drawn on the two previous slides, is this meant to be a process happening in time, say? This is like these are spatial slices and we're seeing—
it's an example. It could or it doesn't necessarily need to be. I just needed to depict like some handle bodies, but I mean, I'm sure you can consider different type of pieces. I just want to emphasize how connected sum requires holding and identification in the middle, and gluing is the conformal boundary glued in together. You could depict in any possible sets, but I thought that's the easiest way of depicting it on the pictures.
So, well, I guess I'm not really asking specifically about the pictures. Are these dynamical processes that you're talking about here? Are these algebraic things?
So we're in Euclidean picture. So first of all, this is not Lorentzian. So your changing will be just based on temperature, right? Inverse temperature as you're in Wick rotated claim. And we're dealing with topology changes. We have not considered like dynamical boundary condition. So far, it's just purely topology changes. Does that answer your question?
Possibly, I'm not sure.
But all I'm actually saying is that you're doing dynamical processes of the Euclidean picture of the baby universes as change in boundary so that it can have a bulk topology changes as currently being dealt with as a combination to bring down to the algebra. But I haven't added geometric picture. Like for example, to deal with dynamical boundary condition, you'll have to do more than this, which I'm going to consider one particular case to do so later.
So this is some sort of operation on algebras. Say like A and B here are meant to be Cstar algebras.
Right. This is going to be utilized to build the Cstar algebra of the baby universe. By that I mean the creation and annihilation of these topological changes that allows us to have baby universe branching out or anything. That will be combined to build what that would give in the level of the operator level for the algebra. Like for example, as I said, I did not put any end of the world brain or anything. This is just purely like a topological level. So moving on with this baby universe operations, this connected sum and gluings, these act the level of the topology of the space-time manifold, as I was just emphasizing now. And then one might think that there's many possible ways to perform them and like however you want. But this is not actually quite the case because you need to remember that we're in a diffeomorphism invariant theories. And these operations will actually inherit structure that's nice due to the diffeomorphism invariance. What I really mean by that is to give an example, when you have the connected sum to consider two different manifolds, it can be uniquely defined in a diffeomorphism invariant theory. So how many large amount of possibilities one might want to consider to perform a connected sum doesn't matter, because it'll be gauged out completely by diffeomorphism invariance. In fact, it actually does better. These connected sums and gluings, these operations, are mutually associative and commutative up to diffeomorphism from its topological properties. So the outcome of considering these operations, which is the reason why I put it in this way, is because it can be performed in a row and many things, but it'll not depend on the order of how it's performed or on which place, how they are performed. So that you can just create it all together holistically to see how many creation and annihilation has been done, and it'll be uniquely defining what possibility can get as an operation standpoint. So now that we have operations of creation and annihilation, now you're ready to build a baby universe algebra, like in quantum mechanics after doing creation and annihilation operators. So here we're going to now have an algebra of observables in the whole bulk quantum gravity as this, which will have a contribution from reservoir algebra, which will be summing over all possible different boundary structures coming from the regular boundary and the conjugate of this. And this is the contribution given coming from the baby universe operations. And as I was saying, the baby universe operations are mutually associative and commutative. This guarantees that this is abelian. Now that's the important part, because I'm going to utilize a lot of properties coming thereof by having this to be an abelian baby universe algebra. So from here, now that we have Cstar algebra already now granted, we can apply GNS construction, and we need a reference state where we cleverly have a KMS state already. So we can utilize that to understand what will happen and can build a Hilbert space thereof. So for here, then we can perform the GNS representation with respect to an abstract state on the algebra observables. And for here, what we really have is that expectation value functionals for it. And in our theory of quantum gravity, what we really have is that the role is played by the gravitational path integral, which is associating to each bulk operator its expectation value by summing over all geometries. So by applying this GNS construction that I explained a bit earlier, what we get is that we are given with a vacuum as a state. So that this is the vacuum, as we are seeing, that's granted coming from the KMS state as I was generating earlier. And you're going to get the Hilbert space, as we did earlier, by modding out all the self-vanishing parts. So that'll be well defined. And this will be the Hilbert space coming from the baby universe contribution. Then, with keeping in mind that baby universe algebra part is a commutative Cstar algebra, and you're given with a state utilizing this, I'm going to now apply a nice theorem by a mathematician called Stormer, that the GNS representation of this baby universe algebra arising from a state has one dimension if and only if this is irreducible. And another way of saying this thing is that if the GNS representation of the baby universe algebra has dimension 1, is that Hilbert space of the baby universe, which was this, is one-dimensional. So then what does it mean to have a state on the Cstar algebra to have an irreducible representation? So here it comes down to what I was motivating in the very beginning, which goes back to purity condition. So the space of states on the Cstar algebra is exactly the same as the space of expectation value functionals on this algebra. And as we all know, the convex sum of the expectation value functional is back to expectation value functional itself. So from there, we can determine that this is a convex space. What does it mean by that is that it has extremal points, especially the points that cannot be expressed as a convex combination of two other ones. Well, this is exactly the same way of saying pure state in an abstract sense, which just means that it cannot be expressed as a statistical mixture of other states. So putting these concretely together as a purity condition, what I can determine as an equivalent statement is that if the Hilbert space of the baby universe is one-dimensional, in GNS language, that means the GNS representation of this baby universe algebra arising from the KMS state has dimension 1. That's identical to the fact that it's irreducible, and that's exactly the same thing as saying the KMS state is a pure state. Now, this is actually going back to then understanding what does it mean by considering an ensemble. Let's actually more precisely explain what that really means. So the space of states on a C-star algebra is a bit more than a convex space. In fact, it has a property that every state on this algebra can be written as a formal integral over the space of pure states for a certain measure for the space of pure states. So in terms of GNS representation, then this will be translated into a direct integral decomposition of the GNS Hilbert spaces as written as this, and this will be then irreducible GNS representations. Now, if you believe that earlier what I said, all equivalent statement is indeed correct, these will be all dimension 1 Hilbert spaces. And each member of this direct integral decompositions, or equivalently the decomposition of the state, determines the one member of the ensemble of theories that is averaged over. So this ensemble contains only one element if and only if the state is pure. So that this is the only possible things, meaning the GNS representation of the baby universe algebra has dimension 1 if and only if it is not given as an ensemble. Then let's actually try to investigate this a little bit more. So this is only then valid to be giving a one-dimensional Hilbert space for the baby universe if the pure state does not necessarily exactly give rise to coming from the baby universe algebra contributions, meaning the restriction of the state coming from the baby universe algebra has to be the one that's pure, meaning that for the state, it will have this composition that requires the purity to come back out. So then what does it really mean in respect to the gravitational path integral if you're allowing this to happen? That means that it factorizes for the path integral formalism, meaning the formation of the baby universes, which is given by this, cannot be influenced by the boundary observables as they'll be given a separate integration sum. And this is also the reason given as analysis by Maroff-Maxfield and McNamara-Baffa when they were analyzed for the baby universes. So this is exactly the identical statement of saying that from algebraic perspective is that its restriction of the state of the baby universe algebra is pure. Any questions? All right. So let's put them all together. So let's say then the algebra of this bulk is given by baby universe algebra being abelian and the regular rest of the reservoir. Then the GNS representation of this baby universe algebra and used by the state is dimension 1, identical to say that Hilbert space of this baby universe algebra universe is one-dimensional, if and only if the restriction of the state of the baby universe is pure. This is a mathematically gotten in together statement as a conclusion, but that's quite the mouthful. So let's try to understand what does it mean physically as a validity conditions that are split into 3 things. So if these are satisfied, then it's sufficient to say that indeed our Hilbert space of the baby universe is definitely one dimension. So first thing will be exactly the same thing, requiring the baby universe algebra to be abelian and can given as this. And you have a pure state on this bulk algebra of quantum gravity. And further, you can now decompose so that you can have a contribution of the baby universe algebra coming from the state. So let's say we actually believe all that and this is all satisfied. Then how should such a state should look like? Because otherwise we wouldn't be able to determine how true that would be. Then I'm going to now re-emphasize again. I'm going to utilize a Abelian feature of this baby universe algebra as a C-star algebra. When such is the case, and we want the state to be pure, that's equivalent to saying that the state is multiplicative. And it's the equivalent thing to say that, meaning it will be splitting into two and it'll still convey the under the multiplications. And this type of state is called the character of the baby universe algebra, as the algebra will guarantee that if it's a character. And this purity condition is then equivalent to saying that the correlation functions of the effects of adding two boundaries actually factorize. This is, in fact, how McNamara-Vafa and Marov-Maxfield looked into, and they argued that this requires a miraculous cancellations of contributions of different topologies in the bulk. Well, that's coming from the analysis of the character theory. Let's see how this is just being granted to be true, meaning this will be just granted to have this happen. So let's look into what does it mean to have an abelian C-star algebra. Abelian C-star algebra is exactly isomorphic to saying the algebra of complex valued continuous functions on a locally compact space. And also it has to vanish at infinity. And the space, being compact, is identical to saying the algebra contains a unit. So it's just called as a Galvan space of algebra and math, so that it can be categorized coming from the algebraic perspective to understand what this compact space is given as. In fact, I'll give in the later examples how you can analyze this and determine what will be possible X that one can guarantee from the given situations of baby universe. And the space of this pure state, which is also known as alpha parameters on this algebra, is exactly evaluation functionals on this compact space, as I was saying earlier. And mathematically, this is isomorphic to the compact space itself. So coming from this, I can conclude that the space of characters of this algebra, realizing the miraculous cancellations in the gravitational path integral, is just guaranteed to be identical to the Galvan space of this algebra. And thereof, miraculous cancellations are just granted from the purpose of algebraic perspective. So let's now jump and try to understand some examples. I'll give two of them. First of them is a topological theory, which was also a theory considered as an example in Marov-Maxfield for the baby universe paper. And in this context, it's very simple. You have one boundary structure, and we have a boundary inserting operator as a path integral called Z, and this is Hermitian. Then adding a conjugate boundary is indistinguishable from adding a boundary. So from here, the idea is that we're going to identify this operator Z with a real variable function. I'm going to put f equals x. And this is real, so it's definitely invariant under complex conjugation. And having together with the constant function of an identity, which is f equals 1, we're going to try to now build a state that represents the gravitational path integral defined on this algebra by this topological theory. And we find that the moment is exactly the Poisson law, as expected. So the state on this Galvan space, which will be a real line here, will be given as just a sum of the Poisson distribution. And here, so far, what I said will actually not apply, because unfortunately, this will not vanish at infinity, because f equals x does not vanish at infinity. F equals 1 does not vanish at infinity. So your state is actually not pure. So what I didn't tell you so far is that instead you can work with pre-Hilbert space and then take a completion to get the Hilbert space, and you can utilize the same analysis to do so by using GNS formalism. So easy fix to this is that without requiring the Hilbert space structure, but performing with the GNS construction with the polynomial algebra generated by this function. And this is actually well defined because all squares of the polynomials have a finite expectation value when integrated against this Poisson density. So that when we take the completion, we'll get everything working and we'll get the Hilbert space going. And this is also very collapsing, though it is not of one dimension because it's not actually pure, and you can demonstrate that it is still not one. Now, so far we've been only doing topological aspects, but we want to understand a little bit more. So let's add end of the world brings to understand a little more dynamical boundary to add some geometric feature to it. So when we do that with the end of the world brings, exactly the generalized Galvan space will be the only modification one required to analyze for the GNS construction. So now, because we have the end of the world branes, we have not just the real line that we took, but we also have a product of a space of matrices together. And by doing that, using some more measure theory, you can have exactly the GNS construction working and get the Hilbert space again, and everything will work. Now let's consider a little bit more involved with an example. This is a QCD theory with a theta vacua. So instead of the Hermitian operator before, now we're going to take this boundary inserting operator to be unitary. And this can be achieved by seeing the conjugate boundary operation as gluing against its corresponding boundary. So the gravitational path integral is performed over topologies with one less boundary than before. Since the operation now of adding boundary has an inverse, because of this operation, it inherits a group structure. So let's call that a group C-star algebra and analyze what we can do with this setup. So the corresponding group algebra coming from this is just linear combination utilizing the number of generators that one require. And the number of generators are exactly the identical thing as the number of boundary structures required to generate the reservoir algebra. So let's say we have k different generators for some finite k. Then this group C-star algebra we get is then given as the algebra of polynomials with this k variables and negative and positive powers. So let's endow this with an involution by taking the group inverse of each group element and the complex conjugate of each other, each scalar, and the norm, because we need to make a C-star algebra, so we need to have a norm. Then this will define a C-star algebra. So we're back into the game. We have a C-star algebra to get it going. So for example, when we have in this setup of the z to the k with k generators, the Galvan dual of this group algebra is exactly the same as Pontryagin dual. And even better, when you're considering k equals 1, your Galvan dual is just a unit circle. Now, when you have k bigger than 1, now you have k free abelian generators. So your Galvan dual is k copies of a unit circle, which would be nothing more than a k torus. Then we can have an observable then belonging to this bulk operator. So it'll have a reservoir contribution and the baby universe contribution, which will have a baby universe action coming from the k independent generators. And due to that, we can actually have this operator to be going through in this process. And we want this to be pure because we want it to be a character of this group as a z to the k. Then it has a multiplicative property, as I was saying earlier. So it divides up. And what you will get as a pure state is this, which then gives us a phase on top of it. So what we actually get in the end is the action of the baby universe transformation, adding a phase parameterized by these alpha parameters that's spanning the Pontryagin dual, which would be u1 to the k, as we have k boundary structures, to the action for the gravitational path integral on this observable. So what we really have to remember here is that we have up till k number of the alpha parameters as a phase. Now this should really make you to remember this really looks like some sort of non-abelian gauge theory. In fact, then we can interpret this as the group of baby universe transformations as the symmetry group overall, associated with these alpha parameters as topological charges. So at least this will be exactly close to the context of non-abelian gauge theories in the Euclidean signature. So for here, then having this to connect to theta vacua will be a interesting exactly same example. So for here, having a non-trivial pi3 as a homology, homotopy group has to be z with for any compact connected simple E group, which we'll take as just QCD for this case, then your phases are always given as e to the I n theta, whereas n is the winding number and theta was a vacuum angle that labels the superselection sectors. And for our cases, by doing this analysis, the analog of those will be the alpha parameters, tagging the irreducible GNS representations, and the winding number is exactly the number of boundaries we are allowed to have as the k. as we were witnessing as here. So we're utilizing the GNS construction to understand the baby universes in the context of ADS-CFT, and we looked into a few more examples that realizes such possibilities. But this was completely done in Euclidean context. So by adding more of a Lorentzian structure on top of it, like inspired with some of the previous paper by Bousseau and collaborators here, using Kahn's co-cycle flow, we're trying to now try to understand that to expand to understand the Lorentzian theories in this context. And GNS construction in these type of operator level things can be applied manifestly to tensor networks. So with Elliott Gesto, I looked into already the pentagonal tilings of the happy code and found in a particular context, you can get a decaying type of correlation functions, but generally not. So one can utilize this to understand more complicated tensor networks, like more complicated happy code, hyperinvariant code, or various others. We also looked into an exact theorem for a generic Hilbert space context, including infinite dimensions, to understand the entanglemetric construction being identical to JLMS formula for relative entropy equivalence between bulk and the boundary. And we're also utilizing this to try to understand for the approximate theorem for it to work. By approximate, I mean the gravitational higher order. So for that, we're trying to look into the diamond norm and utilizing with this GNS technique if that anything can follow through. And by using this type of approach, we're also trying to understand if there exists any, or understanding some sort of quantum extremal surface if possible in this infinite dimensional Hilbert space context. Thank you for listening. If there's any question, I'll be very happy to answer.